Hello. Hello.
Assalamu alaikum, sir.
Am I clearly audible?
Yes, sir.
Yes, sir.
Okay, then we can start our today's lesson. In our last lecture, we have started discussion on data dimensionality reduction in big data settings. And I have mentioned already that specifically for our shallow data, or we can say small data sets, usually we use several data dimension reduction methods like PCA, that is principal component analysis, then LDA, linear discriminant analysis, ICA, independent component analysis. And also we use one of the prominent method is called SVD, that is singular value decomposition. In our last lecture, I have already discussed on it a little, but I want to discuss more on it, specifically how about the data dimension reduction in big data set. In big data analytics for data dimensionality reduction, one of the popular that is decomposition approach is used. We call it the CUR, C-U-R, CUR decomposition. So this is derived from the SVD, that is singular value decomposition process. In our last lecture, I have discussed a little on it, but yeah, at first I want to discuss the CUR because in CUR also we need to apply the SVD. Okay, so I will also discuss about SVD within the CUR decomposition. Then what's the fact here? That is in CUR decomposition, the first thing in SVD specifically, there are some limitations. The first limitation is about the explainability, because in case of the SVD, the data the data set transformed into a new dimensional space, and on the new dimensional space, specifically we can say that the originality of the column names, or you can feature names, we lost those feature names. So we cannot explain exactly that is as those dimensions we already transformed to a new dimensional space. So it is on that case it is tough to explain that is okay, this is that feature. Okay, we cannot say like that directly. Okay, so that's one of the thing. And another thing is about the computational inefficiency. Okay, in SVD, the computational inefficiency, because we have to form different types of matrices, different types of matrices. Specifically, we call it those are in SVD. We have SVD. If we transform our data set, then we need to find out like if a matrix is A, then we have to decompose it into three equivalent matrices. That is called U, and then the sigma, and then V transpose. Okay, so here this U and V, those are unitary matrix. Okay, those are unitary matrix, and here the sigma is the singular values. So we have to represent those in three matrices. So computational cost is high. Specifically, we call it like order of n cube. Okay, order of n cube. So that's why the computational cost is high in that case. The n is number of, we can say, dimensions. So in big data dimensions, we usually work with the higher dimensions. On that case, the n cube is too much. Okay, that's why we have to think about the new approach of solving the same problem, that is data dimension reduction. So in big data setting, that's why the CUR decomposition, one of the efficient decomposition approach, but there are some trade-offs. That means after the CUR decomposition, actually we lose some accuracy also. Okay, but in SPD, those are just the optimal values we usually get from SPD. Okay, so in CUR decomposition, it's a kind of the approximation, and as this is the approximation, that's why we lose some of our accuracies. Okay, now we have to understand what usually we do in CUR decomposition. Okay, the goal is to express A as a product of three matrices like C, U, and R. So we need to decompose the A as a product of three matrices, that is C, U, and R. So we have to select those matrices, that is C, U, and R, in such a way so that we can maybe get that is, we call it the Fabunius error, that is low Fabunius error. Okay, so A, that is A, and then if we multiply this C, U, and R, then if we subtract this C, U, R matrix from A, and then we have to apply the Fabunius norm. Here is the Fabunius norm. Here the Fabunius norm. Then we will get the error. Okay, that is called Fabunius norm error, and that should be small. That means the error should be smaller. So we have to select the CUR in such a way so that we can maybe we can get the minimum error from the original A. What usually you do, if we can discuss it in just in layman manner, then we have to say that we have a matrix like A, and actually the A, this matrix is our data set, and then we have to select some of the columns from A. This is called C, and then we have to select some of the rows from A, and then we have to find out the intersection between these columns and rows, and we have to find out the pseudo inverse of that to find out the U. Okay, so that means we have to select the columns, but we have to apply some policy to select the columns, and then we have to select some rows from this A, and again we have to apply some policy for that, and then we have to find out the intersection between C and R, that is the column and rows, and we have to compute the pseudo inverse of that. Okay, so that will give us the U. So this is the layman description of CUR. That means we have to select some of the columns from the original data set and some of the rows from original data set, and then we have to find out the intersection of rows and columns. The algorithm is given like this. Okay, like the matrix A, this is our data set. This is our data set, and the size of our data set is m times n. Okay, so m times n. So that means we have m instances and n dimensions in our features. Okay, and here is we have to find out that is the C. The C here is our here is the columns in this case. That is the part of the column selection algorithm. Okay, so we have to find out the columns, and how can we find out those columns? These are the procedures for that. Okay, for x1 to n, so here is x1 to n. That means for each and every dimension, like we have n dimensional data, for each and every dimension, we have to generate a probability vector for that. The probability vector, this one we have computed using the summation of Frobenius norms of the the column and the Frobenius summation of the Frobenius norms of the total matrix. Okay, if we divide this one by that, then we will get the probability. Okay, we will get the probability. Let's we can maybe think about one example for that. Think about a data set we have. Let's say we have a data set. Kind of bibliography data set. Okay, like author, maybe we have author author 1. Okay, so author 1, like the individual author 1, and then we have author 2, that is individual 2, and then maybe we have author number 3, and we have author number 4. Maybe in this way we have many authors. And then if we think about like this that is paper published in different conferences, okay, like the conference 1, and here is the conference 2 of the same author, okay, conference 3 and conference 4. We have different conferences. Maybe in this way we can think about like 1,000 conferences, or maybe 100 conferences. Okay, 100 conferences. So if we can now think about our the data set for that is the bibliographic data set for that, for authors and conferences. Then maybe for the first author, that is individual 1, he has a publication in maybe conference 1. Okay, maybe just one publication, and also he has 2 publications in conference 4, and else are just 0. Okay, because usually we can see there is a just one author may be published in like maybe only 5 to 10 conferences, because the domain of the conference is different. So most of the conferences that author will not publish. Okay, so some of the, if we consider one author, maybe the total number of conferences he can attend or maybe publish like maybe within the 10. Then another author, maybe the author number 2, he has no paper in conference number 1, and but some papers in conference number 2, like 2 papers in there, and 3 maybe 1, and 4 maybe 0 and 0, all others 0. For the 3, maybe we can say he has also published one in C1, and he has also published maybe published C2 0, and C1 also just 1, and C4 just maybe 2, and here's the 0, and maybe this conference also 1, like this. And C4, maybe you can say no publications in conference 1, and in C2 maybe 1 publications, and then C3 is 0, and maybe C4 is also 0, and all maybe others just have 1 and 0, like this. Okay, maybe you can say that this is our data set. Okay, this is our data set, one of the source of big data. We can see the dimensions that he used, and number of authors are also huge. So we can consider, okay, maybe we have a large data set for that of huge dimensions. And we can see that there is this matrix or this data set is a kind of the sparse one, because most of the case you will get the 0, and very few you will get just maybe the values are there. Okay. Now what we need to do, if we want to apply the CUR here, that means, okay, this is consider that this data set is a matrix, and the matrix is this is the A, the matrix is A, and we want to apply the CUR decomposition here in this matrix. And for that we have the algorithm here. We can see for x equal 1 to n. So in our case, maybe we have n equal 100. Okay, 100, because we have n dimension, that is 100 dimension, 100 conferences. And then we have to find out the probability distribution for each and every feature. Okay, for each and every feature, for each and every column, every feature. And how can we determine that? Then we can see that is we have to apply the summation of the Frobenius norms. Okay, in this case. So how can we apply that? Now, for the column 1, okay, for the column 1, like we want to find out the probability distribution of this column 1. So that is the column 1. For that, what we have to do, we have to find out the Frobenius norm. Okay, that means we can say it will be, if we can see the equation for that. This is the equation for the Frobenius norm. Okay, here is the x. X is a vector. Like currently our vector is c1. C1 is the vector. Then what's the Frobenius norm of that? It will be the square root of the summation of square values of each and every elements of x. Okay, so that's why we have the C1 here. That is the C1. The Frobenius norms of our C, it will be the value here. First value, first element of this vector is 1, so 1 square plus the next one is 0, so it is 0 square plus then again 1 square and then 0 square. Okay, the summation of all these, and then after sum of these, we have to take the square root of it and divided by, we can see in our algorithm, here we have the I and j, that means I and j for each and every I and j. That means for the whole data set. Okay? For the whole data set, we have to sum up the Frobenius norms. So on that case, it will be specifically, if we can think about this one, then it will be the square root of, there is the 1 square plus 0 square plus 1 square plus 0 square. So that means this is for the column 1, plus we have to think about the column 2 also. That is 0 square plus 2 square plus then 0 square plus 1 square. This is for column 2. Then we have to think about column 3. That is 0 square plus 1 square plus of 1 square plus of 0 square. In this way, maybe think about column 4 also, like it is 2 square plus 0 square plus 2 square plus 0 square. Okay, in this way we have to actually compute up to 100, up to 100. Okay, 0 square plus 0 square plus 1 square plus 0 square. Okay, so then a square root of that. Then we will get the probability distribution for the first column, that is column 1. Let's say, just assume, just this is assumption because this is I didn't calculate it. So let's say this probability is like maybe this one is 0.2. Let's say that's just 0.2. Okay, this is assumption. This is not actual, but assumption. Similarly, what we have to do, we have to find out the probability distribution also for probability for C2. For C2. In that case, we have to think about like this column. It is the second column. So that means on that case, it will be square root of 0 square plus 2 square plus 0 square plus 1 square, and then divided by the same value. Okay, this one, the same. Then maybe let's say this one is just maybe 0.3. Okay, and then similarly we have to think about the like we have to find out the probability of C3. Let's say this one is 0.2 again, and probability of C4. This one is our maybe 0.4. Okay, so in this way we have to find out the probability distribution for the columns. Okay, so that means each and every column will get some probability. That is that is in step 2. So in step 2 we will get the probability distribution. This probability distribution specifically we will get for each and every feature, every feature or every column. Now what we have to do, that's like in third step we can see that is for I equal 1 to C. Okay, see, that is column, the sample columns. So how many columns we want to sample? Specifically, it has also some kind of calculations. So select if we want how many columns we want to select. So that is our the value is C, and it is K is log K divided by epsilon square. So epsilon is very minimum error value. Okay, like maybe it is something like 0.01 or something. Okay, so this is the equation for finding out that is how many columns we need to select. But what is K here? That is K log K. So K log K, it means you can see that is our here is the AK. Okay, AK, that means K is our original matrix, and AK there is the we will consider only kth number of elements from SVD. Okay? From SVD, that means it is kind of, we can say from the large data set we want to select only few columns. Okay, maybe from the large dimension we want to select few dimensions, and this few is called K. Okay, that is we want to select just maybe K dimensions. In our original data set we have 100 dimensions, but now we want to make it like only just 10 dimensions. Okay, so that's our K, the value of K here. Okay, so using this equation we can find out C, but practically we in practice what usually we do, we usually find out the is number of columns equal 4K. So if K is 10, then 4 times of K. Okay, that means we will select maybe 40 columns. Okay, 40 columns. Okay, now so that is our C. That is our C. So here is the C. That is how many samples we want to pick from our original data set. Now, now we need to pick C samples. Maybe you can say 40 samples in this case. C is our that is the 40 samples. 40 samples. And now we want to find out the first sample, that is I equal 1. Then how can we find out that? Now pick J. Here is the J. J is 1 to n. So 1 to n, that means we have n-dimensional data set. So J can be any of these column, like from column 1 to column n, any of this column, based on the distribution px. So here is the thing, that is based on the distribution px. So we have the px, that is the distribution, but how can we select the J based on the distribution? Okay? This is kind of the abstract thing. We need to explain it a little more. That is, how can we pick the J from this distribution? Okay? From this distribution, there are some ways, but one of the way I think we can think about. So for each and every column, like here, for each and every column, we have the initial the distribution, probability distribution. Okay, so let's write those distributions out here. Like for the first column, this one, the distribution is 0.2, and here is the probability is 0.3, and then this one is 0.2, and for 4 is 0.4, and we must have some distributions also here and also there. Okay? For the simplicity, let's say that we have 4 conferences, if we can think about, okay, that's 4 conferences, or we have just these distributions, this distribution, 0.2, 0.3, 0.4, and 0.2 and 0.4. Then what can we do? We can at first normalize this one. Okay, at first normalize this one. How to normalize? It can be the summation. We can sum up all those probability distribution values, like here 0.2, 0.3, 0.2, and 0.4. Maybe the other distributions are not prominent if we consider. And then 0.2, 0.3, here is the 0.4 and 0.3, 0.7. Then it is 1.1. Okay, so that is total summation of those. Sum up with the summation. So 0.2 plus 0.3 plus 0.2 and 0.4. If we sum up, then we can see 4, 6, 6, 8, 8, and then it is 1.1. So this is the summation. The summation of all the probabilities. Now, what we can do, we can divide each and every probability distribution by this value. Okay. So on that case, on that case, we can calculate that values. Like is 0.2 divided by 1.1. It is 0.18. Okay, so this is 0.18. Okay. And the next one, 0.3. So 0.3 divided by 1.1. So it is 0.27. So it is 0.27. And here is also 0.2. That means it will be 1.8. Then here is the 0.4. 0.4 divided by 1.1. So it will be 0.36. Okay, 0.36. So here's the 0.36. Let's say the others are just very negligible. Okay? Now, what we have to do, we have to so these are actually the normalized values. Okay, normalized probability distribution. So now, what we can do, we can think about the cumulative values, cumulative that is values of normalized probabilities. So cumulative values, on that case, we can think about like this one is 1.8, and then for this one we will get what, 0.18 plus 0.18 plus 0.27, and then we will get 0.45. Okay, 0.45. So here is the 0.45. Then we have to add 1.8 after 0.45. So 0.45 plus 0.18. So these are the cumulative values. Okay, cumulative probability. So it is 0.63. Okay, 0.63. And then 0.36. We will get a 0.99. Okay, so 0.9. Okay. So in this way, we will get the cumulative values of our probabilities. Okay, cumulative values of our probability. Now, what we can do, we can see that pick J within this column based on the distribution, based on a distribution P of X. So that means following this distribution, we have to pick like J. Then what can we do? Maybe we can generate a random number. We can generate a random number. Think about a random number. Okay, maybe I can think about like it is 0.3 something. Okay, this is just one random number. I thought it's just a random number. And now we can see that is we have to find out here the interval of this number, 0.3. So interval of this number, actually we can see that we will get this 0.3 within these two values. Okay, so within these two values, so 0.3 will be here, 0.3 will be here within these two values. And then we can see that there is find out the upper bound of our values. The upper bound is what? Upper bound of our interval is this one. This is the upper bound. And then take the column that belongs to the upper bound. So we can see, we can select this one. Okay, select this one, that is column number 2. And this is how we can sample the columns. Okay, so that is pick J this time based on the distribution P. Following this distribution, we pick the J, and now we can say J is 2. Okay, J is 2. So we have picked the column number 2. In this case, we can see that is in C, this matrix. Actually, we have to find out we have to form this matrix using what? Using the columns. Okay? Using the columns, like here. Okay, using the columns. So C, it will be formed using the column, like maybe column A, B, C, like here, some of the columns. Okay, but there are some probabilities that the same column can be copied multiple times also. Okay, because it's the probability. Okay, probability. So you can see that I assume that just assume that the random number, that is 0.3. So I can also think about like, okay, this time 0.2. Again, it will select the same C2, same column. Okay, same column. That's why there is a possibility that we can also select the same column multiple times. Okay, same column multiple times. Okay. So now in this algorithm, we can see that is okay. We got the column, and now what we have to do in our C matrix, we have to insert that column. Okay, insert that column. Now we can see that there is in our A matrix, the J is the column, our column. J is our column, and we have to normalize these values. Okay, normalize these values. So usually, sometimes we convert those values as there is a unit vector, but in case of CUR distribution, instead of unit vector, we uh, we can say that we have converted those numbers. And just maybe we can say we have normalized those values using the probability distribution and the number of columns. Okay, so this is how we have normalized those values. Okay, normalize those values. So that means if we select the J, that means in our case, if we select this column, select this column, then the values is and every values in C matrix in our C matrix. So let's say this is our C matrix. We will add this column C2. This column we will add, but each and every value it will be divided by. So that means 0. It will be divided by square root of C times the probability. Okay, C times the probability. The probability it is 0.3. So C is what? C is how many columns we want to select. Okay, in our case, maybe we want to select the 40 columns. So on that case, we have to divide this one by 40 times square root of 40 times 0.3. 0.3 is an every value we have to divide by that. So in this case, the first value it will be the 0. It will be the 0, and the next one is 2 by 40 times 0.3. So it will be 40 times 0.3 equal this one, and then the square root of that while this one. Oh, sorry. 12. Okay. The square root of 12. 3.464. Okay, 3.464. It is. It is 3.464. And then we have to divide. You have to, the first one is 0, but the next one is 2 by 3.464. Okay, 2 by 3.464. So it is 2 by 3.464. So that is 0.7 and 0.58. 0. Next one we will get 0.58. Then the next one, this value, it will also be the 0. And then another one is 1 by 3.464. 1 by 3.464. Okay, so we will get 0.29. Okay, 0.29. So we will get 0.29. So this one will be selected here. Okay, so this is our one of the column. Now similarly, next time again, so how many columns we want to select here? We can see that is, we want to, this for loop is up to C. So that means 40 times we need to sample columns. Okay, 40 times we need to sample the columns. That means again we have to think about our next just a random probability. Okay, random value. So this time maybe think about, in my case, okay, 0.5. If it is 0.5, so just a random value 0.5. Whatever in my mind, I just tell that. So it is 0.5. So 0.5, that means we have to find out the interval for that. And this time we can see that the interval is 0.5. 0.5 belongs to this interval between 0.45 and 0.6. So we will get 0.5 here, 0.5 here. So then we have to think about the upper bound. The upper bound is this one, 0.63. And then the 0.63, this belongs to our C3. Okay, C3. So we have to think about the C3. We have to take the C3 here. Previously we have taken the C2. It is the C2. Now we have to take the C3, but directly not the C3. What we have to do, we have to find out that is each and every value divided by square root of C and probability of that. Okay, so that means this time it will be the probability, it will be whatever the value, then square root of, we want to select 40 columns times the probability here is for the C3 it is 0.2. Okay, it is 0.2. 0.2. Okay, so that means 40 times 0.2, that is just 8. So 8, and square root of that, square root of 8 is 2.83. 2.83. It will be, we have to divide it by 2. That is 2.83. Then we have to divide. The first one is 0, so 0 is 0, so we will get here 0. And then second one is 1 by 2.83, so 1 by 2.83. So it will be 1 by 2.83. It is 0.35, so we will get 0.35. And then again 1, so we will get again 0.35. And then 0, so 0 is 0. Okay, so that means in this way maybe we need to select here, if we consider our small c value, the c equals 40, then we will get, we need to take 40 columns. Okay, 40 columns, in similar manner. Okay, so I think we understand how to select the columns. Okay, so how to select the columns, that means how to find out our c, that is the column matrix. Okay, now we have to find out our R, that is R is our row matrix. The algorithm is same. Okay, algorithm is same. That means similar way we have to find out the row. So on that case, instead of column distribution, we have to think about the row distribution. Okay? Row distribution. Like in this case, column is n, but row is m. So we have to just consider about the, instead of n for the column, we have to think about now the rows. Rows distribution. Okay, rows distribution. So that means instead of n, it will be m. It will be m. Okay, it will be m. And if we consider this one is y, that is probability of y here instead of x. and then it will be here is the summation. Now we have to think about summation uh, uh, for not for the all I but for the j. Okay, but for the j, and this one will be the same, that is I and j square, and here is we need to think about like instead of x, here is the y. Okay, that means in our example matrix, now what we have to do, if we need to find out the probability of the each and every row, like probability of I1. So the probability of I1, we can put it here. And for that, what we have to do, the similar way, we have to calculate the probability. That is for this row. For this row, the Frobenius norm will be the Frobenius norm. On that case, it will be 1 square plus 0 square plus again 0 square plus 2 square plus 0 square. Maybe lots of zeros are there. Square of the values and 0 square, and square of root of that value divided by whatever we have computed the Frobenius norm of this matrix A. Okay, so that means on that case we have to think about uh, each and every values of this matrix. Okay, of this matrix. Uh, so that is the Frobenius norm of our matrix A. Okay, matrix A. The Frobenius norms of that. Okay. So if we just divide this one, then we will get the value previously. Okay. Just assume. Okay. Just assume that the probability we'll get for this is maybe 0.1, and then for this one again we have to calculate the same. That means the probability distribution for I2, maybe it is 3, and then probability distribution of I3, maybe it is 2, and I4 maybe it is 1, like this. Okay, so if we have M is 4 here, okay, just only M is 4 in our small data set. Actually, in our real life, in big data, there must be many rows also. Okay, so the M is also large enough. So these are the distribution, and again we have to do the same thing as we have done in this uh, the column selection case. Okay, same algorithm, similar manner. It means we have to normalize those values. So how can we normalize that? That is, we have to sum up all those values. The summation here, you can see 0.3 and 0.1 is 0.4, and then 0.567. Okay, so this is 0.7. Then if divide each and every one by 0.7. So in this case, that is 0.1 divided by 0.7. So it is 0.14. Okay, so it will be 0.14. And the next one is 0.3. So 0.3 by 0.7. We will get 0.428, that is 0.43. So we will get here 0.43. And then this one is 0.2, 0.2, so 0.2 by 0.2 by 0.7. 0.7. Oh no. 0.2 by 0.7 is 0.29. So here is the 0.29. And here's the 0.1. That means we will get again 0.14. Okay. 0.1. So that means again what we have to do, we have to find out the we have to find out our cumulative probability distributions. Okay, cumulative probability distributions. On that case, the first one will be the same. The first one will be the same. That means the first one will be 1, 4, and then we have to add the next one, that is the running sum. So it will be 4, 3, 7, and 4 and 1, 5. Okay, and then we will get here 7 and 9, 6 and 8. Okay, and then we will get here is 1. Okay, now again, if you want to select the rows here, if we want to select the rows, then on that case, think about like any probability distribution. Sorry, any probability value just randomly. This time maybe I can think about like 1, 0.1. So 0.1 belongs to maybe within this from 0 to 0.14 within this interval. Then we have to think about like upper value. There is upper bound. Upper bound is just 0.14, and then this 0.14 belongs to our that is our row number 1, the individual one. So we have to select the individual one. Okay, we have to select the individual one. Now what we have to do, we have to select that is the individual one. So individual one, that means these values you can see 1, 0, and 0, 2, 0, and 1.1, like those values. So we can apply again we can apply here each and every value, like maybe the 1 divided by square root of this time r, not the c, that is how many rows we want to select. So in that case, we have the formula for that. That is the R selection. Okay, R selection. We can apply this one, and but in practice, at least we can think about 4 times k. So here's the 4. Our 4 times k. So 4 times k is our 10. Okay, this is also the 40. So R value, R is also 40. But in our case, we have just only 4 rows. Okay, in real life, it will be many, but consider the 4. So the minimum value is 4. So we have to think about all the 4 here. Okay, that means if the minimum of these 2, 4 here. So that's why we will select maybe R number of columns. Let's say the value of R is like we want to select 2 columns only. Sorry, 2 rows only from what it is. So on that case, maybe we will we can consider 2 times then the value of that. Okay, the value probability of that. So probability like this one has the probability 0.1. So each and every value we can think about those probability values. Okay, so that means now we can see that is the first value will be like yes, C1. Instead of this, it will be 1 by 2 times 1. So 2 times 1, it means 0.2, square root of 0.2. 0.2 square root of that is 0.447. Okay? 0.447. So it means 1 by 0.447. 1 by 0.447 will be 1 by 0.447. It will be 2.237. So on that case, maybe we will get 2.237, 2.237, like this. So that means if we want to select the rows, and we have the first row, for the row, we have the first row. In our first row, the first value will be, that is I1, first value 2.223, okay, 223. In this way, the second value, like it will be 0 here, and then 0, and then the 2 is there, so 2 by 447, okay, 2 by 447, so 2 by 0.447, it will be 4.47, 4.47. Okay, in this way we can think about our rows also, okay, like this. So now using the same algorithm, that means similar algorithm, we can find out also, that is the for our row values, okay, our row values also we can find out. But now what we have to do, okay, we can select like row and column, okay, row and column. Now the next thing is, how can we calculate the, here we can say U, okay, so U will be here we can see W plus, then what will be the W at first? So here W be the intersection of sample columns C and rows R. Okay, so that means and the W will be the intersection of sample columns C and rows R. If we consider our data set here, so this is the data set. In this case, we can see that is we have selected like maybe two columns like C2 and C3. We have the C2, this is C2, C2 and C3. So these two columns we have selected, and let's say we have selected I1 and I2. So I1 and I2, like just these two, I1 and I2, these two. Then I1 and I2 means this row and this row, and this column and that column. Okay. Then what will be the intersection? Intersection, we can see that is, these are the intersection. Okay? So this is the intersection. So 0, 0 and 2, 1. 0, 0 and 2, 1. So this is the intersection we have. And here is in our algorithm, it is mentioned there. That is, the W will be the intersection. Okay, W will be the intersection. That means we can say here now the intersection of sample column C and R. What we have to do, this W, we have the W. Now we have to apply. We have to apply the SVD. Okay, that means we have to find out the SVD decomposition values. Okay, SVD, the singular value decomposition of W matrix. So our W matrix, if we determine the singular value decomposition of the W, then we will get, maybe you can say it is mentioned like X and G and Y transpose. Okay, so in SVD, usually this matrix we can factorize or decompose using these three matrices, where the first one is this one and that one are unitary matrix. Okay, unitary matrix. So if we those are unitary matrix, and this G, this is also another matrix, consists of the singular values. Okay, singular values. Okay, singular values. Then for the unitary matrix, specifically we can say a matrix can be unitary if the X transpose of X equal I. That is identity matrix, and Y is also unitary matrix. That is Y transpose of Y. It will be also identity matrix. Okay, identity matrix. And X and Y are also orthogonal. Okay, that is, the X is orthogonal and Y is also orthogonal matrices. So that means two orthogonal matrices we have, and also the singular values in G. So this is our W. Okay, now what we have to do, we have to find out the W plus. So what is W plus? In W plus, what we have to do, we have to transpose this again, transpose this one. In such a case, what we will get? We will get Y. Then here is a G transpose and also X transpose. Okay, G transpose and X transpose. Now, for specifically for this one, G transpose, the each and every, because it is a diagonal matrix, because the singular here, the singular values will be placed in diagonal directions. The transpose of this, it will be just the reciprocal of the non-zero singular column. That means it will be just 1 by of G1, 1 by of G1. So the values we will get here, like if we consider those are just the sigma, like the sigma 1, sigma 2, and then in our G plus, what we will consider? We will consider 1 by sigma 1, 1 by sigma 2, 1 by sigma 3, like this. Okay, so this is called the pseudo inverse. Pseudo inverse. So the W plus will be our U. So this is this is how we will get the U matrix. So it means in our case, so 0, 0 and 2, 1, this is our W. So W here is the matrix 0, 0 and 2, 1. So what we have to do, we have to find out the SPD. That is, we have to apply singular value decomposition. SPD, we have to apply SPD, apply SPD, singular value decomposition here. Okay, so on that case, we will get from here, we will get the X, then G, and then Y transpose. And from here, we have to find out the W plus, that is transpose of this. I get transpose of this, and that is our U. U equal W transpose, which is transpose of this one, and we will get, that is the Y, then G transpose of G plus, and X transpose. Okay, so on that case, this value G plus will be just 1 by G of Ij. Okay, so on that case, we will get the U. So we will find out the U for that case. So now this is how we can calculate. We can compute the U. Okay, we can compute the U. And then there is a theorem for that. Specifically, we can say if we compute the CUR, that is CUNR. If we compute those three matrices, and if we subtract this one from A, that is A is our data set. Subtract this one from our A, and the subtracted matrix, if we compute the Frobenius norm, okay, Frobenius norm of that, and it will be less than this error. That means this error, it will be, the difference is the error, okay, because originally this one and CUR is that. So this one is error, it will be less than the 2 times the error of SVD. Okay? Error of SVD. So it will be less than the 2 times error of SVD, and with the probability of 98%. Okay? So that means, though it will be erroneous, but it will guarantee the error, maybe not the 2 times of that. Then why we apply CUR instead of maybe SPD? That the thing is easy interpretation, because the columns we preserve the same with same name. So that's why maybe those columns have some interpretation. Okay, this is that column and this is that column, the name of the column. So it will be easy to interpret. And here is the sparse basis. That means since the basis vectors are actual columns and rows, it will also keep the sparseness, because you can say that is the original columns. We will just keep the original columns. But what's the limitation here? The limitation here is the duplicate columns and rows. This is the limitation, because based on the probability, the same column can be appeared multiple times. So that is one of the problem here. But there are some solutions also. That means we can drop maybe just those. So we can say throw them away. So if we have some duplicate, then just keep one and throw others. And another one is we can also scale. Okay, we can apply some form of scaling, so that maybe different columns maybe have different scales. Okay, on that case maybe the impact of the same columns, that means same, if it appears multiple times, then usually we can say that has that column or that row has more influence on the data set. Okay, so that's why maybe on that case the influence will be reduced if we scale it differently. So what is the difference between our SPD? Because SPD is also used for data dimension reduction, and CUR, this one is also used for data dimension reduction. But what actually we can see what's the difference. Here, this is the big data. If we consider about the big data case, that is huge but sparse, and U and V in this SPD case, that is unitary matrix or orthogonal matrix. Here, U and V both are big and dense. Okay, here that is the C and R is also there is big but sparse. Okay, because it keeps its sparseness, the values, whatever in the rows, columns, whatever in the rows, the sparseness, it holds the sparseness. But in case of the our sigma, okay, that is singular values, this is sparse and small. Okay, sparse and small. Those values, you will get many zeros over there, many zeros over there. But here in the EU, it will be dense but small in size. Both are small. Both are small. This and this one will be the small. But you will keep the dense. But in case of SBD, it will be sparse. In case of the SBD, what we will get that is a matrix with the singular values. Okay, with the singular values. Usually we name it the sigma singular values, so singular values. But there maybe we will get many zeros, because it's based on the rank of the matrix. Okay, if the rank of our this data set is just maybe 3, then we will get the 3 just 3 singular values, and others will be just 0. Okay, others will be just 0. So that's why it will be sparse. But in case of our U, we have already computed the SVD and the W plus. So that's why the instead of sparseness, we will get the dense values for that. So some of the compactness we will get from here in CUR. So I have already maybe given one example from the DBLP bibliographic data. I think you already understand that. But the problem is here. That is, how can we compute the SBD? Okay. How can we compute the SBD? That is singular value decomposition, because we need it. The singular value decomposition. Now I think it's better if we can discuss the singular value decomposition. How to get that? I think most of you already in your math course you have done, that is SBD. So whatever you have already studied, whatever you have learned, please follow the same procedure to find out this SBD. Okay, but here is one of the theories for SBD, and the steps are also given how to compute that. We can just go through a little of it. Any question? Do you have any question here? Why I'm not listening? Am I audible?
Yes, sir.
Okay. Okay, then if we consider a matrix A, there is A, then let's say any matrix. Okay, let's say any matrix. It is maybe 2, 1, and then 5, 2, like this. Okay. And if we think about one vector like X, so think about one vector X, and that is also kind of 1, 2. Consider this one. So if we multiply this vector with this matrix, that is, if we try to find out that A X, if we multiply these two, then we will get 2 times 1 is 2, and 1 times 4. Okay? So that is 4. 4, and then 5 and 2, that is 9. So here 4 and 9. Okay, 4 and 9. Okay. It means if we can think about, like, we have this vector, there is a vector X. This vector X is 1 and 2. Let's say this is 1 and this is 2. And then we can draw our vector. This is the vector. Okay, this is our vector X. Okay, now we can see if we multiply this vector with this A, that is with this matrix, then we will get another vector. Okay, this is the vector, resultant vector. You can see in that case it is 4 and 9. Maybe you can say 1, 2, 3, 4, and 9 maybe. Okay, maybe we will get like here. Okay, the vector will be like this. Okay. Let's say the vector will be like this, the 4 and 9. 4 and 9, this vector. So it means that is this is a vector. This vector, if we multiply by any matrix, then actually what it does, actually it scales. Okay, it scales. That means we can say it's increased the length, and also it's rotated to somewhere else. So that is our kind of the scaling and rotation. Okay, so specifically it has some scaling, and then like from this length it will scale up to this length. Okay, so that's why it's scaling, increase the length, and then it also rotates some. So it has some rotation. Rotation. Okay. Rotation. Now if we think about our the vector, this vector, like orthogonal vectors. Okay, like this is, I can say v1, and this is our v2. These two vectors are just orthogonal vectors. So here the v2. Then if we multiply this vector with a matrix like A, okay, this with this matrix like A, then actually what it will it will do, what will be the output for that case? So we will at first maybe the scale, so that means it will be large. Okay, after scaling it will be maybe large in size like this, and then so on the scaling may not be the same size. Like we can see that is the different vectors maybe have different type of scaling. If we have the similar scale of v1 and v2, then maybe we'll get the circle. And if we have different scales, the like v1 has a scale differently, v and v2 scale differently, on that case what we will get, maybe after scaling we will get some elliptical shape. Okay, like this one. Maybe on that case the v1 is scaled like this way. This is you consider u1, and the v2 is scaled like that way, maybe that way. Okay, so this is our u2. Okay, and also the rotation, it will rotate according to our matrix. So it means we can represent this phenomenon like, in our case we have orthogonal v1 and v2. So in this case, if we think about A, our matrix, and we multiply our one of the vector, that is the v1, then usually what we will get, it will scale. Okay, it will scale. Let's say the scaling factor here, the scaling factor is sigma 1, and e1 will get. Okay, so e1. Okay, so we will get like a v1 equals sigma e1. Okay, similarly for u2 we can also write a v2, it will be like maybe sigma 2 and u2. Okay, so if we can expand this phenomenon, like we have a and then maybe we can think about this matrix, and then we have a set of vectors like v1, and then maybe the v2, and then maybe the v3. In this way, maybe we can say we have many, okay, vn up to. Then what we will get? We will get the sigma 1, sigma 2 like this way, okay? That is sigma 1, sigma 2, and also e1, e2. So we can write this one as the e1, then maybe the u2 in this way, maybe up to un, and then we have that is the sigma 1. Okay, so for the sigma 1 we can represent this one as a matrix. This is a sigma 1. I think should write a little bit different way. Okay, then we can write for the sigma, we can write a diagonal matrix like here. This is sigma 1 and this is sigma 2. In this way, maybe we have up to sigma n, and all other all values are just 0. Okay, just 0. So here the 0, 0, and 0. So this kind of matrix. Okay, so that is so e1, and here it will just, if we multiply this one with that one, then we will get sigma 1 e1, and that is a v1 equal sigma 1 e1, and then a v2 equal sigma 2 u2, like this way. Okay, so this is the representation. So in this case, if we can say that actually it is a, and this is our v. Okay, so here is the v, then this is our u, this is our u, and then this sigma is our matrix sigma. Okay, and then what we can write here a equal u, then sigma, then v inverse. Okay, v inverse, v inverse. So, but we know that there is the, if v is our orthogonal matrix, then the inverse of that is equivalent to the equivalent to our transpose. Okay, because this is the properties of the orthogonal matrix. So we can write it like u and sigma and v transpose. Okay, v transpose. So that means a, this matrix, we can decompose into three matrices, u, then sigma, and then v transpose. Yeah, u and v, those are orthogonal and unitary, and sigma is it holds the diagonal singular values. Okay, singular values. So this is the derivation of, that means a can be expressed using u, sigma, and v. Yeah, that is our SVD. That is our SVD. But how can we find out the u? How can we find out the sigma? And how can we find out the v matrix? For that, how to calculate that? For that, the algorithm or step is given here. So what we have to do to find out the SVD, that means to find out these three matrices, that u, sigma, and v. What we have to do? The steps are, at first we have to compute A transpose A of a real m into n matrix of A. Okay, so that means A transpose of A we have to calculate. So A transpose of A, that means we can see A, we have the dimension is m into n. If we transpose it, then what we will get? If we transpose this one, transpose it, then we will get A n into m. Okay, and then another A, we have to multiply it with A. So A is A m into n. So if we multiply this one with A m into n, m into n, then the dimension will be dimension A transpose of A. The resultant matrix dimension will be, let's say, x. The dimension will be n into n. Okay, I think we know that is. So this is n. There is also n. So that is n into n. We will get n into n. So this is the first step, and then compute the singular values of A transpose A. Then how can we do that? Specifically for that case, we have to find out the singular values. The singular values are the square root of eigenvalues. Okay, square root of eigenvalues. So the singular value, that is sigma I, sigma 1, is square root of eigenvalues. So now what we have to do, we have to find out the eigenvalues. Eigenvalues of what? Eigenvalues of this A transpose A, this matrix. That is our, we can say, the X matrix. We have to find out the eigenvalues of A transpose A. So again, I think you know how to calculate the eigenvalues and eigenvectors also, because we need also the eigenvalues and eigenvectors. So I think if you know that already, then it's fine. Just apply the same principles and method to find out the eigenvector and eigenvalues. But we have a lecture sheet on PCA, and on that sheet you will find out that is how to compute the eigenvalues and eigenvectors. Like the example is given, and the steps are also given there. Okay, the steps are also given there, like how to compute the eigenvectors and eigenvalues. So on that case, the given matrix, whatever the given matrix, we know that to find out the eigenvectors, we have to have the square matrix. Okay, the square matrix. That's why it's the n into n identity matrix, and the dimension of the same dimension. Okay, so we have in our resultant matrix, we can see this is n into n. Okay, so that means we can find out the eigen values and eigenvectors of this matrix, because this is a square matrix. Okay, a square matrix. So how to do that? The steps you will follow here: multiply n into an identity matrix by a scalar, then subtract the identity matrix multiple from A. I think no need to discuss this, because I can assume that anyhow you know how to compute the eigenvalues and eigenvectors. Okay, there are several maybe tutorials you will find out here and there, and as this is the one of the undergrad courses we have, specifically on mathematics, linear algebra, we have already learned how to compute the eigenvalues and eigenvectors. I think just go for that. Otherwise, you can also follow my lecture on PCA. I will share that also. Principal component analysis. On that lecture, I have this detailed discuss, that is how to compute the eigenvalues and eigenvectors. Okay. Okay, then here is the compute the singular values from this matrix. This matrix is a square matrix, and we can find out the singular values will be the square root of the positive square root of the eigenvalues, that is positive values. So lambda I. Okay, lambda I. Then we will get what? We will get the sigma 1, sigma 2, sigma 3, sigma 1, sigma 2, and sigma. Then sort the singular values, that means this one, possibly renaming by the sigma 1, sigma 2, sigma r. That means we have to sort these sigma values in ascending order. In ascending order. In PCA also, we have to sort the eigen values in ascending order. The same sigma is also we have to sort in ascending order. And then construct the sigma, that is this matrix. Now we have to construct the matrix using these values. Actually, we have to put all those values in diagonal directions. That is, if we consider this is our matrix, then the sigma 1 we have to place here, then sigma 2 here, and then maybe sigma 3. And all the remaining positions we have to just fill up with just zeros, okay? Zeros. So we can see there. So possibly the renaming them and then construct these values. We can see that we have to place the sigma in their diagonal direction and other direction just 0. Okay, when I not equal 0, then we will get the sigma sigma matrix. And then what we have to do, we have to compute the eigenvectors. So that means the for each and every eigenvalues, we will have the corresponding eigenvectors also. In step 5, you have to find out the eigenvectors, and then compute the right singular vector. That is, we in our case, the right singular vector is what? The right singular vector is this one. This is right singular vector. Okay, this is Vt. This is Vt. We have to we want to compute that, and for that what we have to do, if we consider the Si, this one is our eigenvector for the eigenvalue, that is the lambda I, then we have to divide this one by the length, okay, length of that vector, the length of that vector. Then we will get Vi. We will get the Vi. Similarly, for each and every eigenvector, we have to find out this characteristics vector of our right singular vectors. Okay, right singular vector. So right singular vector is just we have to divide the eigenvector by its length. It's kind of unit vector. Okay. Now what we have to do, the next thing is using that we have to construct the orthogonal matrix. That means the V1, V2, Vn up to Vn. Here we have already got the Vi, V1, V2, V3 from our eigenvector, and then we will calculate the V. Okay, we got the V, and then we have to verify, that is whether the calculated V is actually orthogonal or not. So if it is orthogonal, then V transpose V, we will get the identity matrix. Okay, so this is just the testing case. Now we have to find out the left singular values using this kind of relationship, or we can say that or alternatively what we have to find out, like this time A dot A transpose. Previously what we have done, compute the eigenvectors of A transpose A, but for finding out our U, this U, what we have to do, we have to compute now the eigen values and eigenvectors for this one. Okay, let's say this one is our Y. Okay, A transpose, and previously A transpose A transpose and A transpose A. Okay, why actually this one? Because I think, yeah, we have the explanation, because A and A transpose is what? We know that there is A is our U, sigma, and V transpose. Okay, then we have A transpose. So A transpose is U, sigma, and V transpose, and transpose of it. Sorry, the transpose of it. So if we do the transpose, on that case, it will be U, sigma, V transpose, and then it will be the here the V transpose, and transpose of that we will get the V, and then sigma, and then U transpose. Okay, so that means we will get what U, and then here is the sigma. This is V transpose and V, actually the I. So identity matrix. If we multiply something with identity matrix, then it will be the same matrix, that is sigma. And here is the sigma transpose also. Okay, sorry, transpose also. So here is the sigma and sigma transpose, and then U transpose. Okay, so we can see now we have just U and U transpose here. Okay, so that means we can now find out the U. So here is the sigma and sigma transpose. This is our sigma square. We will get the sigma square. Okay. So now what we have to do? We have to find out the eigenvalues and eigenvectors of A transpose. Similar way, we have to compute now the UI. It will be the one by, there is SI and also the SI. Okay, so UI from that. So that means we will get the vector also for the left singular matrix, that is U matrix. Okay, left singular matrix. Then after that, test that one, that is U transpose is I or not. So if U and U transpose is I, then verify that is A, whether this combination will give us A or not. Okay, yeah. Then what we have to do now, we can think about the decomposition. That means instead of taking all the sigmas, here we can see for this one we have maybe a matrix consists of sigma 1, maybe sigma 2, and sigma 3, and maybe sigma 4. So those sigmas are actually their strength. Okay, so that means this value will be the higher than another all other values, and this value will be higher than sigma 3 and sigma 4, but lower than sigma 1. Okay, so all other positions are just 0, we know. Okay, like this way. Okay, so on that case, what we can do, we can just maybe think about like we can just only take, that is the 2 dimensions one, sigma 1 and sigma 2. So that means consider just only these two, and discard all others. On that case, what we will get? We will get maybe there is kind of approximation of A, not the actual A, the approximation of A. Okay, approximation of A. If that approximation is sufficient or not. If that is sufficient, then I can maybe use that one and discard all others. Okay, discard all others dimension. So it will reduce the dimension of our data. That means maybe we have the 100 dimension, but using just only 2 dimension, it will sufficient for our case. Like one example is given. Here is the example. If we consider this is our A, then how can we find out the SVD? Following that step. Okay. And another example is given, that if this is the A, then how can we find out the SVD? Okay. Okay. Now one real life example is given, like we have this. This is the original image. So this is our A. And we have computed the SVD there. And then if we consider about n equal just 1, so that means our just one is with the sigma 1. So if we use that to generate this figure, then this will be like this one. Actually, the difference is huge for that case. But if we consider our maybe the just 10 dimensions, the 10 dimensions. So this pixel's dimension is huge. It is given here. The dimension is total maybe this one, this much maybe 100 and 200. Okay, 100 times 200. So that means 200 dimension, 100 times 200 dimensions. Like if we consider 10 dimension, then we will get this kind of picture. This is the approximation of this one. If we consider n equal 100, that is 100 sigma, then this is the approximation. So we can see this is close enough, okay, close enough. Instead of using maybe 780 dimensions, the total dimensions, we can maybe use any approximation like this one, 100. On that case, only 13% data is required to represent the same image, okay, same image. Instead of like maybe considering all. If you need more clearer version, then maybe you can say you can use like 500, n equal 500. On that case, maybe you need just 64% of the data instead of the all the data for that case. Okay, so this is how the SPD can also reduce the data dimension, help reduce the data dimension. And this SPD in our CUR algorithm, CUR decomposition, this SPD is used here. Okay, the same SPD to find out the U. I think that's all in our that is big data decomposition dimension reduction methods. So do you have any question or queries? If you have, then we can discuss. Otherwise, maybe we can finish our discussion. Okay, I think no question from your side. So that's all in our today's lectures. Thanks for joining here. Thank you very much. See you in your next lecture.
স্যার
হ্যাঁ বলো।
স্যার লাস্ট লেকচারের আজকের লেকচারের ভিডিওটা যদি একটু আপলোড করতেন ড্রাইভে খুব ভালো হতো স্যার।
আচ্ছা, আজকের লেকচারটা হ্যাঁ এখনই আপলোড করতেছি। লাস্ট লেকচারটা আমি ইউনিভার্সিটিতে ছিলাম, ওখানে গিয়ে আপলোড করতে হবে।
ঠিক আছে স্যার, ওটা একটু করে দিন।
ওকে ওকে, ঠিক আছে, থ্যাংক ইউ।
স্যার
অ্যাটেন্ডেন্স সবার।
আচ্ছা স্যার, লাস্ট ক্লাসে কি অ্যাটেন্ডেন্স দেওয়া হয়েছিল?
ওই সবার দেয়া হয়েছিল।
ওকে স্যার, জি থ্যাংক ইউ স্যার।
ওকে।